All right, thanks everybody for coming back today on the second day of remote instruction. I know it's a big challenge for everybody, and I appreciate that you're joining me in the synchronous session, coming in live with me. So what I want to do is just sort of review, just kind of recap where we were yesterday. We finished up the energetics portion of the lecture. We talked a little bit about kinetics. We went back, talked a little bit about thermodynamics. We talked about the things that affect the rate of a reaction. So that was increasing the temperature and adding a catalyst. And we sort of talked about how those things happen. When it comes to the temperature, we talked about the number of molecules that have enough energy to get over the activation barrier. And when it comes to catalysts, we talked about how it provides a different pathway for the reactants to reach the products and that different pathway has a lower activation barrier. Then we introduced the concepts of what electrophiles and nucleophiles are. Essentially, electrophiles are things that like electrons. So that means they're either positively charged or partially positively charged. We talked about nucleophiles, and nucleophiles are things that like nuclei, and nuclei are positively charged. And so if you like something that's positively charged, that means that you are negatively charged or you have a partial negative charge. That brought into the idea that not only are there nucleophiles and electrophiles, but there's also nucleophilic and electrophilic sites in different molecules. And a particular molecule might have both a nucleophilic and electrophilic site. And so eventually, especially in chapter 7, what we're going to have to think about with a particular reagent is whether that reagent is nucleophilic or electrophilic, and then what other kind of chemistry that it can do. After we finish with nucleophiles and electrophiles, we started to talk about mechanisms, and that's where I want to start today. And so I'm actually going to start recapping mechanisms with the different mechanistic steps. And so we introduced that we basically said there's 4 different types of mechanistic steps. And these 4 mechanistic steps are essentially the only things that you're going to come in contact with throughout the entirety of Organic 1 and Organic 2. So it really is important for everyone to become familiar with these 4 possible moves, because at the end of the day, these are the only 4 moves that you're going to employ in a particular mechanism. When we think about an acid-base reaction, it's essentially just a proton transfer. So there's really only one step in the mechanism. But later on, especially if you're going to move on to Organic 2, there's going to be mechanisms that have 3, 4, 5, even 7 steps. And one of the ways that you can employ to remember what the steps of the reactions are is to think about which of these 4 possible moves are there in the mechanism and in which order they come in. In other words, down at the bottom left of the screen, you could say, well, maybe there's a proton transfer, a nucleophilic attack, a proton transfer, a loss of a leaving group, and a proton transfer. And you can remember a more complicated mechanism just by remembering the abbreviation. It's kind of a mnemonic of what are the different steps. And so what I want to do is I'm essentially going to start over with that and go a little bit slower than I did on Tuesday, because I know that I went through it a little faster at the end of the lecture. And so I want to make sure that I recapture some of that information and kind of get us back to where we were. Once I finish with the stuff for chapter 6, I'm going to pause the video, and then we're going to go back to that worksheet so that we can take a look at that that mechanistic problem and see if we can sort that one out. Then what I'm going to do is I'm actually going to stop the video. We're going to take a 5-minute break, and then we're going to come back into the meeting, and then we're going to start chapter 7. So it'll be a hard break into chapter 7. All right, so these mechanistic steps. Proton transfer. Nucleophilic attack. loss of a leaving group. And then rearrangements. We went over all of them briefly, but I want to make sure to kind of revisit them. Now, proton transfer is the thing that you're familiar with. Proton transfer is essentially the step, the mechanistic step involved in all acid-base reactions. So if I take something like benzoic acid and I mix it with something like hydroxide, then there's a proton transfer. Benzoic acid is acidic, sodium hydroxide is basic, and so the hydroxide will want to take the proton from the acid, or another way to look at it is the acid will want to give the proton to hydroxide. The reason that I prefer the perspective that the hydroxide wants to take the proton is because remember that when we do mechanisms, when we draw arrows, we're always drawing them from the perspective of the electrons. We spend a lot of time talking about the definition of acids in terms of protons, the Bronsted-Lowry definition, but really at the end of the day, mechanisms are always done from the perspective of electrons, and so that's the way I prefer to talk about it. So in this case, what we're going to say for a proton transfer is that the electrons from the hydroxide will grab the proton or take the proton or form a bond with the proton. And if that's going to happen, then at the end of the day, the electrons that are already connecting the proton to the benzoic acid, they have to move back onto the oxygen. And so if I want to draw the products, I'll show the negatively charged oxygen on the benzoic acid, and then finally the water product as well. I think we're all familiar with this one, and so what I'm going to do is just pause a beat. If anybody wants to raise their hand, then I'll throw, we can take a pause, and if anybody has a question. All right. So what's new are the 3 steps after proton transfer. One of them is nucleophilic attack. And I know that I started to talk about carbocations yesterday, and we're going to spend a lot more time talking about them today. But a carbocation is a place where there's a carbon that's missing a hydrogen, and so therefore it would have a positive charge. If I have a similar situation where hydroxide is in the solution, hydroxide can also have its electrons attack the carbocation and form a bond with that carbon that was sp3 hybridized. So a new bond is formed. So part of the thing with nucleophilic attack is that a new bond is formed. Well, that's fine with nucleophilic attack. This one is pretty straightforward, but I want to also point out that nucleophilic attack can happen even with things that are neutral, things that already have a full octet. So carbonyl groups are something that we talked about yesterday. The oxygen is electronegative, and so it's partially negatively charged. The carbon then would become partially positively charged. So from the terms of nucleophiles and electrophiles, we would say to ourselves that the carbon in a carbonyl group is an electrophilic site. It's partially positively charged, and the oxygen is nucleophilic. And so depending on what reagents are in the I like to call it the pot, the proverbial chemistry pot, depending on what reagents are in that pot, you would say, okay, which one of these sites is going to be more likely to be reacted with? Let's say that I have ammonia in the pot, and ammonia can be a nucleophile. And so we can show a nucleophilic attack to something that's already neutral like this. Now, remember that a nucleophilic attack involves the formation of a new bond. if I were to draw a new bond to that carbon without doing something to the double bond on the carbonyl group, I'd be violating the octet rule. And you know, when you violate the octet rule, Dr. Cotton gets frustrated and points come off. I'm trying to be funny, but it's so hard without any instant feedback. I'll just assume in my mind that everybody is hilariously laughing. Yeah, there we go. Laugh and chat, that does it for me. All right, so the long story short is that if I were not to do something with this carbonyl group, then I'd be violating the octet rule. So oftentimes, nucleophilic attack not only involves the arrow that shows the nucleophilic attack, but it involves a second arrow that shows some sort of relief that maintains the sanctity of the octet rule. So if I were to take a carbonyl group and have a nucleophile like this attack it, it would still end up having a tetrahedral intermediate. But since I moved the double bond from the carbonyl up to the oxygen, it would now have a negative charge. And since I attacked the carbonyl group with a ammonia, it would become attached, but now it has a positive charge, right? Because 4 bonds to an ammonia has a positive charge. Now, later on in the reaction, we can go and we can take care of these charges. Proton transfers can happen, and these things can get more complicated. But at the end of the day, what I'm trying to illustrate with a nucleophilic attack is that there's more than one possible thing that can happen. Okay, so I'm going to stop right there, make sure, take a beat. If anybody has any sort of questions, go ahead and type that in chat as well. Or raise your hand and I can stop that video. All right, cool. So at this point, what we've done is we've talked about 2 different things. We've talked about proton transfer and we've talked about nucleophilic attack. And so the next thing that I want to do then is talk about loss of a leaving group. Loss of a leaving group is what makes, oh, let me back up a second. I did miss something with nucleophilic attack, so let me uncheck that and let's do one less little bit. Nucleophilic attack can happen with electrons that aren't lone pairs. And so if I have something like a nitronium ion, then it's possible to have a nucleophilic attack with the pi electrons. So I could have a nucleophilic attack like this. Now, there's the same situation as before, where the nitronium ion already has 4 bonds, so I'd have to show some sort of relief. And so what I forgot to mention was that nucleophilic attack can happen with lone pairs of electrons, but it can also happen with, with pi bonds. All right, so this is what I missed. I wanted to make sure that I show you guys that you don't have to have a lone pair. You could have a pi bond as well. That'll also do a nucleophilic attack. So let me stop there, make sure I didn't confuse anybody terribly. Okay. Now I can put a check mark. Ah, erased it. Now I can put a check mark there. All right, so let's talk about this loss of a leaving group business. All right, so a loss of a leaving group is when something that we will just collectively refer to as a leaving group leaves a molecule and it takes its electrons with it. Now, what the problem is that you're gonna later on, you're gonna have to ask the question, what's a good leaving group? At the end of the day, only good leaving groups leave. And one of the things that you're going to have to do as chemists, as really, really awesome organic chemists, is determine which kind of group that's attached to a molecule is a good leaving group. If something is not a good leaving group, it won't leave. That doesn't mean that you can't make it leave by turning it into a good leaving group. It just means that that's what you're going to have to do something in order to make that happen. But in its simplest form, we can show that a leaving group involves something leaving a molecule and taking its electrons with it. So in the simplest example, we can talk about how something like bromine could leave a molecule and form bromide and form a negative ion and a positive carbocation. Now, most of the time, it's not that simple. Most of the time, it involves more than one arrow, just like loss of leave, just like nucleophilic attack. We could have something like this. There'd be a negative charge here, a negative charge there, a positive charge there. Maybe there's a chlorine here and an OH there. A loss of a leaving group could be accomplished through a more complicated series of electron movements. And one of the things that you really are going to, that's going to be incumbent on you to do is to get used to the different possible electron movements and thinking about what's a good leaving group and what's not a good leaving group. So it could be as simple as example number 1, but it might be more complicated like example number 2. Does anybody have any questions about that real quick? I want to pause a beat because that's all I want to say about loss of a leaving group. Okay. So I feel like I have earned my check mark there. All right, so now we're getting into this really serious business, which are rearrangements. The reason it's really serious business is because the rearrangements involve carbocations, and carbocations are where we left off yesterday. Now, what I want to talk about is, and spend a little bit more time talking about, is what a carbocation is, what are their stabilities, and then why would they rearrange? All right, so a carbocation is a carbon with a positive charge. So in order to have a positive charge, the carbon must be missing a bond. And that bond can't be replaced with a lone pair of electrons. If it was replaced with a lone pair of electrons, it would be a negative charge and it would be a carbanion. So here we are with a carbocation. This is a methyl carbocation. You could have a carbocation that is attached to another carbon. This one would be primary, and it's primary because the carbon that is a cation is connected to only one other carbon. So that means that there are, as well as primary carbocations, we could have a carbocation that's connected to two other carbons. And you could imagine that we could have a carbocation connected to three other carbons. And likewise, we'll call this one tertiary. And so this is usually the point in the lecture when I say, why can't we have a quaternary carbocation? And this is where you all raise your hand and you get really excited because you all know the answer. And I'm going to pretend like you're all doing that right now, jumping up and down because you all know the answer. But you can't have a quaternary carbocation because that would imply that it's bound to 4 other. It's not. It would imply that it's bound to 4 other carbons. If a carbon is bound to 4 other carbons, then it's not a cation, it's neutral, right? Exactly. Not an anion, it's neutral. Now you could make it an anion if it had a lone pair of electrons, but it would be neutral if it were connected to 4 other carbons. All right. Okay. Now I put the carbocations in the order that I have them in on purpose. And the reason that I have them in this order is because this is the order in which they are stable. So the methyl cation is the least stable of the cationic trend. Then it goes primary, then it goes secondary, and then it goes tertiary. So the next part of the lecture is to discuss why it is that a cation that has connected to more carbons would be more stable than a cation that's connected to no carbons. And so what that's going to require me to do is redraw. And so let me erase and come in here. And what I want to do is I want to redraw it, but I want to use our nice 3-dimensional perspective. So if I were to say, what was the hybridization of a carbocation, I would get inundated in chat with a bunch of people writing sp2. Good job. Right. It's sp2. There are, yeah, exactly. There are only 3 bonds, and something that has only 3 bonds will be sp2 hybridized. And when I say 3 bonds, I really mean 3 electron groups. Even though this is a cation, it still only has 3 electron groups, and so that means the hybridization is sp2. We can think about that hybridization being sp2, which means that the 3 bonds are sp2 hybridized orbitals. And so what that means is there's an empty p orbital. In a carbocation. Now, I've drawn a picture of the methyl cation. And what I want to do now is I want to draw a picture of the methyl cation. And what I want to do is I want to change it. I want to change it to a primary cation. So if it's a primary cation, what I'm going to do is I'm going to include the CH3 group on the other side. So why is primary more stable than methyl? Here's the vocabulary word. And this is a vocabulary word that I and almost every other organic chemistry professor will want you to repeat. Is the reason is hyperconjugation. What is hyperconjugation? Hyperconjugation is this ability for an adjacent sp3 hybridized orbital to share electron density into the p orbital that's empty. So if I have a cation and somehow that cation is able to get a little bit of negative charge, just a little bit of electron density, then that little bit of electron density goes to stabilize that empty p orbital more than if it's in the situation where there's a methyl group and there is no ability to stabilize that positive charge by adding electron density. So hyperconjugation is adding electron density from adjacent sp3 carbon-hydrogen bonds. That's what hyperconjugation is. And so then if this explains why a primary is more stable than a methyl, then why is a secondary more stable than a primary? Well, if I take this idea and I expand it out and I add another cation, the question was asked, would I ask this kind of question on an exam? And I'd say, certainly, this is fair game, right? So I might say something like, a common question would be, here are some cations. Rank them in order of increasing stability. Why is it more stable? Why is the most stable cation more stable than the least stable? And so you might invoke the idea that, well, I've picked the tertiary cation as being the most stable. It's the most stable due to hyperconjugation. And that's about as much in Organic Chemistry 1 as I'd ask from you. In Organic Chemistry 2, I might actually ask you to draw the diagram that I'm asking. Or excuse me, draw the diagram that I'm drawing. And so when we think about why a secondary would be more stable than a primary, we would replace that hydrogen with yet another CH3 group. And that means that there is now more opportunity for an adjacent sp3 hybridized bond to donate electron density back to that empty p orbital. The same thing would happen if I were to talk about it in terms of why is a tertiary more stable than a secondary. It's for the same reason. If I have yet another group that's a CH3, I'll have a third opportunity to donate electron density back to that empty p orbital. And so this is an illustration of why a carbocation that is connected to more carbons is generally more stable. So what I want to do is I want to pause just a beat and see if anybody has any questions about that, because there's one more situation that I want to talk about when it comes to cation stability. All right. So I want to put this order back again. So it was methyl, less stable than primary, less stable than secondary, less stable than tertiary. But there's two other types of cations that should be included on this list. And that's this cation. And this was a cation that we explicitly talked about in one of the previous discussions in the lecture, or way earlier on in chapter 2. Why might this cation be more stable? It's in a primary position, but yet it's still more stable than the tertiary cation. Does anybody see what's going on right here? It has a pi bond that's directly adjacent. Yeah, it's directly adjacent to that positive charge. So this cation is resonance stabilized. Resonance stabilized cations are more stable than tertiary cations. And there's two different types of resonance stable cations. This one is allylic, and allylic means one spot or place removed from a double bond. There's also another one, and it's called benzylic. Maybe there's two L's there. Again, I'm going to totally embarrass myself in front of the entire world by showing them that I can't spell. Yeah, it's going to be funny. Benzylic cation is essentially the same situation as an allylic, but it involves being one space removed in a benzene ring. In this particular example, I can show that the positive charge, although it appears as if it's outside the ring, can also be delocalized into the ring. And if you notice with a benzylic cation, there are several different structures. And in general, if you remember from this idea of resonance, the more resonant structures there are, the more stable the cation is. And then I could show the last one where this one comes down here, and that would get me back to there. And so typically only primary or secondary carbocations undergo rearrangements. We don't have to worry about rearrangements with resonance stabilized cations because essentially they are as stable as they can be. Rearrangements happen when a cation that is less stable becomes a cation that's more stable. And so if we think about it from an energetic perspective, if I have a primary cation and it can become a secondary cation, then this is energetically favored. When I say more stable, I mean lower energy. And so this is, real quick, a review. Is it thermodynamically favored or kinetically favored? That's a cue for you to type into the chat. Yeah. When I talk about the difference in energy, I'm talking about thermodynamic favorability. So remember, kinetic favorability talks about the height of the barrier. Thermodynamic favorability talks about differences in energy. Nice little review there. Good job, Eric. All right, so let's actually talk about rearrangements for a second. Does anybody have any questions about cations in general before we talk about rearrangements? All right, cool. All right, so what's up with a rearrangement? Let's say that I have a primary carbocation. What's a rearrangement? A rearrangement is a situation, is a mechanistic move where a carbocation that is unstable becomes a carbocation that's more stable. The first type of rearrangement that you have to deal with is a 1,2 hydride shift. In a 1,2 hydride shift, it's called 1,2 because it goes from one spot to an adjacent spot. So if you're thinking about naming, it would be 1,2. Now that's not the name. The name isn't 1,2, but we're just saying that the hydride shifts from one carbon directly to the carbon next to it. Remember what a hydride is. A hydride is a negatively charged a hydrogen atom or a hydrogen ion. If it's negatively charged, it's got both electrons. So if I show a hydride shift, I show the electrons from the bond to the hydrogen moving to the adjacent carbon. So the resulting product in this case is to put the CH3 group at the end and put the carbocation in the middle. So we go from a primary to secondary position. This is one of the types of shifts, of one of the types of rearrangements. Now, you could have a situation like this. Let's get this correctly. What if I have a cation like this? Right now, everybody's saying, oh, that's a secondary carbocation. How could I improve the stability of this cation by making it a tertiary? Cation. There's a different type of shift. This one is called a 1,2 alkyl shift. And an alkyl group is a group that has a carbon on it. And so if you look at the adjacent carbon, the carbon to the left, there isn't a hydrogen to do a hydride shift. All of these things are CH3 groups. No worries. We can still take the entire CH3 group and move it over. This would be a 1,2 alkyl shift. And in this particular case, it would be a methyl shift. And so the resulting product would actually have the methyl group move to this location to then form the tertiary carbocation here. This is significantly important because it actually changes the connectivity. And we spend a lot of time talking about connectivity when it comes to when it comes to molecules, because if I'm changing the connectivity, it's like an actual, it's almost akin to isomerism. In a reaction, we might actually have a situation where the connectivity of the carbons changes because of the desire, or because of its desire to form a more stable cation. And so this is it. This is what a rearrangement is. And so I'm going to go ahead and give myself a check mark there, and I'll pause a beat. It's still here. So the question was asked, what happened to the hydrogen? That's still there, right? And so that's what makes this particular carbon neutral now. It's got 4 bonds. It had one hydrogen attached to it. The methyl group moved all the way over to that spot where the hydrogen is, and now this carbon has 4 bonds, so it's neutral. Cool. Any other questions? The question was asked, why is it tertiary? It's tertiary because since this was the spot, switch up to a different color. This had been the spot that was the cation. And this carbon is connected to this CH3 group and that carbon. And since it's connected to 2 other carbons, it's secondary. After the methyl shift, This carbon became neutral. So it's no longer the spot where the carbocation is. This is the spot where the carbocation is. It's attached to a CH3 group, a CH3 group, and now this carbon over here. So it went from being secondary to tertiary because it's connected to 1, 2, 3 different carbons. Is that good? Cool. All right, so let's try to put it all together, and then we'll take this little break to do that. Example. So here's an example of how this could all work in a more complicated sense. Here's an example of a proton transfer. What would be the resulting structure from that proton transfer? There. Now what? First one to type the result, this mechanistic move in chat gets $1. I did. I got a charge on it. Yeah, that's exactly right. This is a loss of a leaving group. So I did a proton transfer. I did loss of a leaving group. What do you notice about this third structure? This is a secondary carbocation. Can it become more stable by doing a rearrangement? Yeah, I have the possibility of doing a shift, in this case, an alkyl shift. Uh-oh. The important thing to think about now is, where is the charge? Where is the charge? Charge is here. Remember that if I have a carbocation, then this guy, there's a hydrogen at this location, so it's already got 3 bonds. And so this is a rearrangement. And if I have a bromide in the solution, the bromide can attack the carbocation, form a new bond, and that was obviously nucleophilic attack. So that's putting it all together. Does anybody have any questions about those mechanistic moves? All right, just a couple of reminders. Remember that when we draw arrows, we always draw them from electrons. We always draw them from electrons, whether that's a lone pair of electrons, or remember that it can be drawn from a pi bond. So we could have a mechanistic move that looks like that, where those electrons move over and you're showing resonance. So that's one thing to keep track of. We always start an arrow from electrons. We always point arrows to atoms or to other bonds. If we point them to atoms, as in this case, we're showing that a new bond is formed. If we point them to bonds, what we mean is that a single bond goes to a double bond. The last thing I want to point out is we never take arrows and they never jump over groups of atoms. So arrows are, so I would never do something like, if I had, that's not possible. This is a bad arrow. There's a lot of reasons why it's a bad arrow. One of the reasons is it's just violating the rule. I said don't skip over a bunch of atoms. We only move things one step at a time. And plus, I can't form a double bond here because there's already a couple of hydrogens. I can't form one there because there's already a couple of hydrogens. So what I'm going to do is I'm going to pause the video, and then I'm going to unmute everybody and kind of let everybody relax and ask any questions. And then what I want to do then is get on